Okay, let's continue our discussion. So here we have example 7.5. The planet Mars has two moons, Phobos and Deimos, and Phobos has a time period of 7 hours 39 minutes. So in the first case, time period is given 7 hours 39 minutes. Okay, and orbital radius is given. That is, R is given here 9.4 into 10 to the power 3 kilometers. Calculate the mass of the Mars. Okay, so we know law of periods. Time period square equals to something constant, and the constant is 4 pi square divided by universal gravitational constant times mass of the body about which the revolution is taking place. Means here the mass of the body, that is the body is Mars here, about which the revolution is taking place. And then r cube. Look, this r is orbital radius. If we are choosing that the orbit is circular and it is semi-major axis, if we are choosing the orbit to be elliptical. Okay, so in case of circular orbit, so whatever it be, here we have r given. Now from this thing we have to obtain this value m. So we can write mass of the Mars as 4 pi square, okay, this is r, divided by g, and r cube divided by t square. And then we can write 4 pi square, pi, let's take 3.14 square into r square. Okay, let me convert it into SI system. So it will be 9.4 into 10 to the power 6 meter. Because look, we are going to choose the constant, gravitational constant g in SI system. So if we are keeping all these things in SI system, the mass will be in kg. Okay, here we can write 7 or 39 minutes. So we can write it 7 into 60 minute plus 39. This will be in minute. And how much it will be? So 420 plus 39 minute. And we can write 459. So 459 minutes, or you can write into 60 second. So here we will have r equals to 9.4 into 10 to the power 6 meter and cube divided by capital G, which will be 6.67 into 10 to the power minus 11, and SI units will be there. And then time period square means 459 into 60 square. And then this value, whatever it be, unit will be kg. So the only thing which is a bit lengthy here is the calculation. So you have to do it by yourself. And let me write the answer directly here, and it should be 6.48 into 10 raised to the power 23 kg. This much. Okay, let it be. Okay, now moving to the next part. Assume that Earth and Mars move in circular orbits around the Sun, with the Martian orbit being 1.52 times the orbital radius of the Earth. What is the length of the Martian year in days? Okay, so here we have given in the second part, we have radius, orbital radius actually. So this orbital radius of the Earth multiplied with 1.52 will give orbital radius of Mars. Means radius of uh, Mars, radius of the orbit of the Mars around the Sun, and this is radius of the orbit of Earth around the Sun. Okay, this is one thing. Now, time period we can say in case of Earth, time period is 365 days. So, as we know, this thing. T square by, okay, let me write it, mass divided by Te square equals to R ms cube divided by R es cube. So again, we have a difficult part here is the calculation only. So we have to put all these values. Let me write it. This will be 1.52 cube, because this ratio RMS by RES will be 1.52 into 365 square. This is what. And then you can get T, time period of Mars, equals to 1.52 3 by 2 into 365, this much. Okay, so this will be in days, because here we have chosen this thing in days. So this is example 7.5. Now let's move to the next example. Here we have example 7.6. What we have to do? Weighing the earth. Okay, you are given the following data. G is given 9.81 meter per square second, and radius of the earth is given 6.37 into 10 to the power 6 meter, and the distance to the moon is given, R is given 3.84 into 10 to the power 8 meter, and the time period of the moon's revolution is given. So T is given here 27.3 days. Okay, obtain the mass of the earth in two different ways. So first way we can obtain T square equals to G 4 pi, not G, 4 pi square divided by G, mass of the earth, and R cubed. Remember, this is time period for the moon, this is orbital radius for the moon, and this is the mass of the body about which the moon is revolving, that is mass of the earth. So from here we can obtain mass ME will be 4 pi square divided by G, and then R cube by T square. Look, again we have to do the same thing here. We have to convert this thing into seconds. So how can we do that? This is in days, so we have to multiply it with 24, then it will be in hours, and then 3600, it will be in second. So the same thing we have to do here. This will be 4 into 3.14 square divided by 6.67 into 10 to the power minus 11, and this is in SI system. And then R cube will be 3.84 into 10 to the power 8 cube, and then this will be 27.3 into time period square, so into 24, now it is in hours, and then into 60 into 60, now it is in seconds. So we have to solve this entire thing, and then the mass will be in SI system, that will be in kg. So I am leaving the calculation part to you, because it will just increase the length of our discussion here. And okay, I am writing the final answer here. So mass of the earth through this method, we are going to get nearly 6.02 into 10 to the power 24 kg. Now, let's say this is the first method. Now, let's go for the second method to obtain the mass. So, we know acceleration due to gravity can be written as g into mass of the earth divided by radius of the earth squared. So, from here we can write mass of the earth equals to g radius of the earth square divided by capital G. And look, radius of the earth is given and it is in SI system, and G, acceleration due to gravity, is given, it is also in SI system. So everything is given here, and capital G you know already. So the only thing you need to do, you can put all these values which are required here, and then you can calculate, and then you are going to get 5.2. 97 into 10 to the power 24 kg. So using two different methods, you are going to get the mass of the Earth nearly same. Look, this is nearly 6 into 10 to the power 24, and this is also nearly 6 into 10 to the power 24 kg. Okay. Now let's move to the next example. Look, these examples are very easy. The only thing you have to do is to bear with the calculation part. That is a bit lengthy here. Okay, express the constant k of equation 7.38. Okay, the equation I'm writing here, this is nothing but t square equals to something constant into r cube. And if k is given in terms of 10 to the power minus 13 second square per cubic meter, we have to calculate it in days and kilometers. So this is not very difficult part. You can do it. Second square, so you can write 1 by 3600 hour square. And then meter, you can write 1 by 1000 kilometer cube. Now you can calculate this part, and then it will be nearly, again, the calculation part I am leaving to you. You have to do it with utmost care, and it will be nearly 1.33 into 10 to the power minus 14 day square divided by kilometer cube. Okay, so after getting the value of k, now we can move to the next part. The moon is at a distance of this much. So r is given, or vital radius, you can say 3.84 into 10 to the power 8 meter. Here 10 to the power 5 kilometer, I have directly written. Obtain its time period of revolution in days. Okay, so the better thing we can do here, we can keep this thing in kilometer only. So let me write it in kilometer, because look, here we have chosen this constant in terms of day and kilometer. So keeping this thing in kilometer, we are going to get time period in unit days. Okay, so time period square equals to k, which is 1.33 into 10 to the power minus 14, and r cube, that is 3.84 into 10 to the power 5. And look, this is in kilometer, this is in day square per cubic kilometer, so it will be in day square. So you can further go and write this much. And now again there is calculation part, and I hope you are going to do a little exercise and you will solve it by yourself. This will be in day, and then nearly it will be 27.3 days.